and today I'm going to continue with some more properties of Möbius transformations. So, as I said last time and today, what I'm going to do is I'm going to somehow take an arbitrary Möbius transformation. From that Möbius transformation, somehow I'm going to pass to a standard example. And these geometric properties that we found, I'm going to push them. Now, defining a standard example starting from an arbitrary Möbius transformation, this I'm going to do the next lecture. What I'm going to do today is I'm just going to study how the pushing works. Okay, so the pushing will itself be achieved by Möbius transformations. Okay, but somehow the point of view today is that these Möbius transformations are the ones that I'm going to use to push to study the arbitrary one. Okay. So this is kind of this is really going to be a kind of a tool to later on study arbitrary Möbius transformations. Okay. So we already saw that the Möbius transformations of the complex projective line form a group. And now I'm going to start saying some words about the group structure of the Möbius transformations of C bar. Right? So it should be expected that if somehow the Möbius transformations of C bar are really somehow defined by simply taking the normal forms of the one-dimensional vector subspaces and just writing the formula with respect to these normal forms, it should be expected that this is really going to be a group isomorphic to the original one, right? Like essentially the same group. I mean, in particular, a group. Right? So that's what I'm going to start with. Then a fundamental theorem, which is this simple transitivity on triples of distinct points. So if you give me two triples, each one consisting of two ordered triples of points in C bar, each of them consisting of three different points of C bar. So ordered and three different. There is exactly one Möbius transformation that takes first one in first one, second in second, third in third. Okay, and this is really a fundamental theorem for the whole theory. And then we're going to see that Möbius transformations send circles to circles. So in a way, they don't distort the geometry too much. Right? So circles of C bar to circles in C bar. And then disks go to disks. This is going to be kind of an easy corollary of this. Then we're going to very briefly study an invariant. So an invariant for the action of Möbius transformations. And then if time permits, I'm going to see this simple transitivity as a P1 shadow of a phenomenon in linear algebra. Okay. So let me start with this with the group structure. So as I said, we already know that the Möbius transformations of the complex projective line form a group. This we already know. I mentioned it. I mentioned it in the review, right? And it was actually an exercise to be handed in on Wednesday. And now, kind of, we are just going to round up the picture for C bar. So, if you give me an ordered basis of C2 and an invertible 2x2 matrix with complex entries, remember that we have the homeomorphism phi of B which goes from C bar to P1C, right? And it really is phi B of Z is, and there are two cases. This is when Z is equal to infinity, right? And this one was V1, right? Where B is V1, V2, and the other one is this Z, V1 plus V2, right? So then Z and C, right? So the what I've been mentioning all throughout, and then this is very easy to check. In other words, if one just computes mu of the matrix, right? So it's mu A of Z would be equal to alpha Z plus beta divided by gamma Z plus delta, provided that the matrix A is equal to alpha beta gamma delta, right? But that is exactly the same as taking the linear map multiplying by alpha, and then because that one has A itself as its matrix, and then just that linear map somehow it's P1 shadow, just write it in terms of the standard basis, right? So this is a not standard basis. With respect to this basis B, sorry. Anyway, so this is very easy to check, and so what we have now for matrices is if I want to compute the composition, right? Which kind of in what you find in the books is that they do this computation, right? Mu of B. So let me write it: mu of B, mu of A of Z, and then let's say this is mu B of alpha Z plus beta gamma Z plus delta, and then this would be let's say A alpha Z plus beta divided by gamma Z plus delta plus B divided by C alpha Z plus beta gamma Z plus delta plus D, right? And then and then somehow like one starts you just doing the computation and rearranging things, right? And then, but actually, one would have to actually be strictly speaking careful, because if this could be zero, but not only that, this could be zero, and so on, and take special cases and so on. And this is exactly, somehow that's exactly what I wanted to avoid. That's exactly why I started with the definition of Möbius transformation in terms of linear maps, right? Because now I can simply use this formula, right? So I substitute mu of B with the corresponding one, and mu of A with the corresponding one. Oops. This one cancels, right? So I just rewrite, and then you see here what I have is the Möbius transformations of linear maps. So these are really Möbius transformations of P1C, of the complex projective line. And over there, we already know that we can take the composition after or before taking the Möbius transformation. Right? So this is equal to this, and right, and then you see this linear map is multiply this linear map is multiplied by the matrix A and then by the matrix B. So it really multiply by the matrix BA. Right? So I can substitute this with this, and then I notice that you see that this I can substitute with just mu of BA. Right? So I could avoid all these computations and then just say, okay, so mu of the product of the matrices is precisely the composition of mu of the matrices. Okay, and then this automatically implies that that I have a group homomorphism, right? From GL to C to all the self homeomorphisms of C bar. Well, I mean, to the group of bijective functions from C bar to C bar, and one would have to check continuity. Continuity, I leave it as an exercise. But now, knowing that the Möbius transformations of C bar form a group, well, I just denoted mob of C bar, right? Similar to how I denoted mob of the complex projective line. Yeah, so here there's an exercise, and actually, when one considers C bar as a Riemann surface, right, with the two charts that we saw, right, which one was well, recall we gave two charts. In one chart, it was just the open subset C of C bar together with the identity to C, and in the other chart we had C bar minus 0 together with the chart Z goes to 1 over Z. Okay, and then with respect to that structure of Riemann surface of C bar, we define the notion of holomorphism. So the exercise here is that to show that it's precisely the Möbius transformations arising from 2 by 2 invertible matrices. It's precisely those are the holomorphic maps from C bar to C bar, which are bijective and whose inverse is holomorphic. Okay. So some formalization, something formalization of what I've been saying about taking kind of about having the Möbius transformations to be defined kind of in terms of the normal forms of the one-dimensional subspaces. Of course, fix a basis, right? And then I have this commutative diagram, right? So, does everyone know what a commutative diagram is? Yeah. Yes. Yeah. Yeah. Sorry. Sorry. Okay. Yeah. So starting with the linear map, one can take its matrix with respect to the given basis, and once we have this basis, once we have this matrix with respect to the basis, we can take the Möbius transformation of that matrix, right? So somehow it's kind of from F we take the matrix which would be my alpha, beta, gamma, delta, and then from that we obtain this formula. We obtain just the formula, right? Z goes to alpha Z plus beta divided by gamma Z plus delta. This would be this composition, and this other composition would be, well, first just take the map that to each one-dimensional subspace it sends each one-dimensional subspace to to its image on the ref, right? That would be this, and then just write the one-dimensional subspace, which is the image. Write it in normal form with respect to V, right? And if you make the computation, what you obtain is precisely that formula, right? I mean, not if you do the computation. We actually did the computation. So, okay. Now, something to be noticed is I mean, these vertical arrows, they depend on B, right? But you see, but this one doesn't depend on B, the correspondence rule, and the correspondence rule of this one also doesn't depend on B, right? So this means that somehow the Möbius transformations here and the map that assigns to each bijective linear map its Möbius transformation, and the map that assigns to each matrix kind of the Möbius transformation given by Möbius formula, they really live as independent entities. Right? They really are as mathematical objects. They really are independent from one another, and it's for each given basis that I can establish a connection between the two. Okay, and somehow, and the commutativity of this diagram, what it's really telling me is that the way what we did of finding an explicit formula for Möbius transformations defined with linear algebra, finding the normal form with respect to a basis, it really is the P1 shadow of just taking the matrix representing the linear map with respect to a given basis. Okay. Okay, and now I have these two group homomorphisms, and somehow what I would like is to find its kernel, find the kernel of this one and the kernel of this one. Why would I want to do that? Well, this map is surjective by definition. By definition of this group, this map is surjective, and by definition of this group, this map is surjective. These two groups, and in particular this one, are very concrete groups. Right? I mean, they really are defined. You know, these are just 2 by 2 matrices, right, of non-zero determinant. I mean, they are like really concrete. This one is a bit more abstract, but still very concrete. But so if we find the kernel, for instance, of this map, then by the first isomorphism theorem from group theory, we would have that this modulo the kernel would be isomorphic to this one, and somehow that would give me kind of a concrete way of thinking about the group I'm interested in. Right? So that's why I want to find the kernel. Unfortunately, the kernel of both of them is very simple very easy to. It has a very simple description, and it's both just the non-zero multiples of the identity. So somehow the obvious thing. If you think of, for instance, of the rule here, which is, you see, a goes to mu of a, and mu of a of z is alpha z plus beta and gamma z plus delta. Something that should be realized automatically is that if I multiply alpha with any non-zero complex number lambda, say, here let's say lambda, here what I obtain is lambda. Oops, let me do it always on the right. What I obtain is lambda, but lambda here, lambda here, and so the lambda cancels, right? So mu of lambda of A of Z is equal to mu of A of Z, right? So in other words, mu of A is equal to mu of lambda A for all lambda non-zero, right? In particular, mu of lambda times the identity matrix is just the identity of C bar, right? So somehow, at least, we know that multiplication by non-zero complex numbers doesn't modify the Möbius transformation. And so we know some obvious elements of the kernel, and what the theorem says is that's the whole kernel. That somehow kind of the obvious thing is already the whole kernel. And in particular, we have this both this and this are isomorphic to this quotient of GL2C. So which is very nice, because this what we obtain is a very simple description up to isomorphism of my two groups. So it's kind of a just invertible matrices modulo you are free to multiply by non-zero complex numbers without changing your transformation. Right. Let's see about the proof. So something right. So kind of, yeah, it suffices to show that for for any matrix, the Möbius transformation associated to it is the identity, if and only if it's a multiple of the identity, right? And somehow I already argued why this is the case for every lambda. Now I only have to show that if a matrix gives me the identity Möbius transformation C bar, then it is a non-zero multiple of the identity matrix. Right? So okay, so we compute in 3 points. So if mu of A is the identity, then of course it sends 0 to 0. Right? But then mu of A of 0 is simply beta divided by delta. Right? And since this is 0, well, I know that delta is not 0, and that beta is, then it has to be 0. Right? So what I obtain is this entry has to be 0. Next, since mu of A is the identity, it sends infinity to itself, right? But mu A of infinity, as we said, it was just the limit when Z tended to infinity. And that limit, the limit of what? Of alpha Z plus beta divided by gamma Z plus delta when Z tends to infinity. But when Z tends to infinity, right? I mean, it's kind of just coefficient of the leading term divided by coefficient of the leading term, because both the numerator and denominator have the same degree. Okay, right? But then this is alpha divided by gamma is infinity, so it must be the case that gamma is 0 and alpha is not 0. Okay, so from these two, what I obtain is I'm a kind of in the good direction, right? So now I only have to verify that alpha and delta are equal. I know they are not 0. I only have to check that they are equal. Okay, but now I see mu A of 1 is 1, because mu of A is the identity. And for 1, I just plug 1 in the expression of alpha Z plus beta, gamma Z plus delta. Right? So I plug it in, and I know that this one is 0 and this one is 0. So alpha is equal to delta, because alpha divided by delta is 1. All right, and then I'm done, right? I mean, now what I arrive is 0, 0, and these two are equal. Well, A was a non-zero multiple of the identity matrix. And second, I mean, as a corollary, what I obtain is, well, this is just because of a basic group theory. I know that once I computed the kernel of a group homomorphism, I know that the preimage of any point in the image of the group homomorphism is just a member of the preimage times the kernel. Right? So when I translate that fact from group theory to my specific groups, what I obtain is that two matrices give me the same Möbius transformation if and only if, well, if and only if, right, mu of A is equal to mu of B, but this happens if and only if mu of A, mu of B inverse is the identity, and this happens if and only if mu of A P inverse is the identity, because taking Möbius transformation is group homomorphism, and this happens if and only if this is in the kernel. This happens if and only if this is lambda times the identity for some non-zero lambda, and then I take back B inverse. Right? So I just pretty much redid the proof of this fact from group theory. Okay. Now notice this is now very important. Here my analysis was, you see, it's enough. Actually, forget about this. It's enough to assume this to obtain my my conclusions. So somehow I didn't even need to know that this was the identity. All I needed to know was that 0 goes to 0, infinity goes to infinity, 1 goes to 1. And then I could deduce that A was a non-zero multiple of the identity matrix, and that implies mu of A equal to 1. So somehow this property can be deduced already from just fixing these 3 points. Right? So I write it as an observation, as a corollary. If a Möbius transformation fixes 0, 1, and infinity, it is automatically the identity function. Okay. All right. Now, the next result has to do with trying to still obtain all Möbius transformations, but with a smaller group. Okay, and this smaller group is just the matrices of determinant 1. Yeah. Okay. So I think I think I will. It will become more clear why I would want to do that later on. When we speak about the Möbius transformations that preserve the upper half plane. For the moment, it's kind of, let's say, just for fun, like try to find a smaller group that still gives me all Möbius transformations. I mean, a Möbius transformation, let's say at the level, let's say here, a Möbius transformation of P1 was the P1 shadow of a bijective linear map. Right? And here a Möbius transformation of C bar is by definition mu of A for some invertible matrix with complex entries. And the question I'm saying here in particular is it possible to obtain any Möbius transformation here with a matrix of determinant 1? Right? Not kind of already not arbitrary, but with a specific property of having a determinant 1. And the answer is going to be yes. Right? So if you take a 2 by 2 complex matrix, of course, yeah, here I should have written the determinant. Sorry. So here is the determinant. I can, of course, divide by the determinant, which is not 0. And then the determinant of this matrix is already 1. Okay? Because of this multilinearity of the determinant, right? I mean, I'm multiplying A with some scalar. The scalar enters in both rows. When I take the determinant of that, first I take one out from one row, so I take it's one. I take it out one time, and then the next time I take it out again, and then the square root can. I mean, it's a square root times itself, right? And then it's the determinant of the rest, so it's determinant 1. Right? So that's why I have to take the square root. Here again, square root of the determinant. Yeah, so it has determinant 1, and, well, I'm multiplying by a non-zero scalar, so the Möbius transformation doesn't change. Right? So the Möbius transformation is the same. So every Möbius transformation can be realized with through one dimension, through not a one dimension, so through a matrix of determinant 1, and then I have this surjective group homomorphism. And then when I ask it about its kernel, what do I get? I say, okay, its kernel must be all, you see all the elements here that go to 1, but all that go to the identity, but it should be all the elements that are here and are non-zero multiples of the identity, because this map is still the same as before. Okay, but then when I compute the 2 by 2 matrices with determinant the 2 by 2 matrices with determinant 1 that have that are non-zero multiples of the identity, I realize that it's only plus and minus the identity. And so what I obtain is that my groups of Möbius transformations are isomorphic to PSL2C, which is just SL2C modded out by this subgroup that has only 2 matrices. Right? And here I can say, okay, so here I think it's, yeah, here it's clear why I would like to do that, because what this is telling me is that the group of Möbius transformations is almost a group of matrices. You only have to take the quotient by a 2-element subgroup. So you see, this is almost the trivial subgroup. So this looks almost like a group of matrices. That's my point. All right, are there questions? So let's move on to this simple transitivity on triples of distinct points. And the simple transitivity is, as I said at the very beginning, what it states is that if you give me 2 triples of points, 2 ordered triples, so let me write here, these are ordered triples. Of distinct points of C bar, and each triple consists of 3 distinct points. So that's what this means. That these 3 are different, and these 3 are different. Although of course there could be some overlap between this and that. That's allowed, but not a self overlap. Right? Well, whenever you are in that situation, there is exactly one Möbius transformation taking the first one to the first one, the second one to the second one, and the third one to the third one. Okay, so let's see the proof. And first, it suffices to prove the theorem, assuming that one of the two triples is a concrete triple, namely 0, 1, infinity. Why? I mean, the reason should be easy to see, because somehow I would be, you know, I'm kind of I mean, why does it suffice to prove the case here? Because once the theorem is proved in this case, what we are going to have is that for any other triple W1, W2, W3, I can kind of plug it into 0, 1, infinity. But then any other triple, I can plug it into 0, 1, infinity, and then I can go from one to the other. Right? At least at least the existence, at least why the veracity of the proof of the theorem in this case implies the veracity of the proof in the existence for two arbitrary triples. So that should be clear. And uniqueness. Yeah, uniqueness. So you see, in uniqueness in this case, how does it imply uniqueness in general? Well, if there were no uniqueness in general, there could be two triples where there are two Möbius transformations connecting them, right? But then two Möbius transformations connecting them, and then I go to 0, 1, infinity, and I obtain two different connecting these two to 0, 1, infinity. And then I would not have uniqueness in this special case, right? So I pretty much solved the exercise for you, right? So it is indeed sufficient to prove the theorem in this case. And then here it's a bit unfortunate that we have to divide into cases, right? So first, suppose that infinity doesn't belong to this one, and that's actually kind of the I would say it's the most generic case in a way, right? I mean, infinity really is kind of a super special point in C bar, right? But it's only one point. So if you give me three points in C bar kind of at random, the most likely is that none of them is going to be infinity, right? So this is really the case that dominates. Okay. Okay, and then what can one do? I mean, one wants to send. So I mean, here is some formula, but the point is, but how do I get that formula? One wants to send W1 to 0. So one wants Z minus W1 in the numerator, because when I plug in W1 instead of Z, it vanishes and it gives me sends W1 to 0. Okay, and then I want to send W3 to infinity, so I really need Z minus W3 in the denominator, right? And then I realize, okay, I need something more, because when I plug in when here I plug in W2, well, I do not necessarily obtain 1. How do I obtain 1? Well, put this here and put this here. Right? So this way, at least kind of I cooked up a way of sending my 3 points to 0, 1, infinity. And now the point is, okay, is that a Möbius transformation? And well, fortunately, yes, right? Because somehow, I mean, this I just multiplied here and here, and also here. I mean, I distribute both numerator and denominator, and what I obtain, you see this one going here and here, and this one going here and here. It really looks like a Möbius rule. Right? And what Möbius rule? Well, with Z, these two numbers, and without Z, is minus W1 times this, and here is minus W3 times this. Okay, and the point of this is a 2 by 2 matrix with complex entries, because these are complex numbers, because infinity is not any one of them. And does it have non-zero determinant? Well, kind of, you just compute it, and it doesn't have and its determinant is not zero. Right, and I mean, and you see, it's non-zero. It's not zero precisely because these three are different. Okay, so you see, the determinant is this times this minus this times this. You see, this one is so the determinant becomes this times minus W2 minus W1 times right times sorry minus I'm getting a bit lost. I'm just going to do it because so the determinant, you see, this one goes out, so it's W2 minus W3. This one goes out because it's common factor, so it's W2 minus W1, and then times, and then here I have a 1, so times, here I have a 1, here I have a 1, so times times minus W3 plus W1 minus W3 plus W1, and so it's precisely the differences between the 3 points, and all those differences are non-zero because these three are different. Okay, so this is indeed in GL2C, and so this formula that I cooked up does what I want, and is a Möbius transformation of a matrix. Okay, that was case one, and so more or less then I know what works, right? I know what trick works. Notice that this can be applied in explicit examples, right? I mean, if I give you specific W1, specific W2, specific W3, you can even write a program, right? That gives you this matrix. Okay, now case two, I know what to do. Suppose that infinity is one of them, and then again, infinity can be the first one, infinity can be the second one, or the third one. Okay, let's say that it's the first one, and remember that I want to send the first one to 0, the second one to 1, and the third one to infinity. Right. So I still have z minus W3. Right. I want to send W2 to 1, W1 to infinity. So let's see, what can I do? So let's see. I want to send infinity to 0. Right, infinity to 0. So it's observe, infinity to 0, but infinity has to go to alpha divided by gamma. So alpha, I take alpha equal to 0. I take alpha equal to 0, and then in the denominator, I take z minus W3. Right, and I want to send W2 to 1. Right? W2 to 1. So let's say that I put here a 1, and then when I plug in W2, I get W2 minus W3. Okay, so then I know what to do. So this has to do W2 minus W3 And I think that's it. If I did things correctly. So yeah, infinity goes to 0, Z3 goes to infinity, and W2 goes to 1. Yeah, so it's correct. And now check that it is indeed a Möbius transformation. So let's see. Let's see what matrix we can write. And so 1, W3, W2, W2 minus W3, 0. Right? Determinant of this is W2 minus W3, so it's indeed invertible. Okay, if W2 is infinity, so remember 0, 1, infinity. So W2 is infinity. So I still want W3 to go to infinity. So Z minus W3. I want W1 to go to 0. So Z minus W1. And I want W2 to go to infinity. So W2, when I plug in W2, sorry, I'm doing it the other way around. I want infinity to go to 1. Sorry. I want infinity to go to 1, which means I just leave it like this. Right? Yeah. Yeah, and then I check, yeah. W1 goes to 0, W3 goes to infinity, infinity goes to 1, and this is associated to 1, W1, oops, sorry, minus W1, 1 minus W3. Determinant is minus W3 plus W1 is not 0. Okay, and finally, if W3 is infinity, so infinity has to go to infinity, which means that gamma has to be 0. Right? So gamma has to be 0. Okay, W, and then here Z minus W1. And when I plug in W2, I want to obtain 1, so I have to put W2 minus W1 here. Right? And then this is the Möbius transformation associated to 1 minus W1 at 0, W2 minus W1. Determinant W2 minus W1, it's non-zero. Okay. Now, I did this kind of explicitly, kind of in front of you, so that you can see that it really can be performed. That it's explicit computations. You can actually program all of this. Okay. So let's prove uniqueness. Right. So recall, we are still working in this special case. Right. But you see, so let me think. Right. Suppose there were two Möbius transformations that send W1 to 0, W2 to 1, and W3 to infinity. Suppose there are two of them, two Möbius transformations doing that. Then I can take this composition, and it would not be the identity. But it would fix 0, it would fix 1, and it would fix infinity. And we said that if a Möbius transformation fixes 0, 1, and infinity, then it has to be the identity. Right? So uniqueness really follows from this corollary. Okay. Some very useful corollary is that you see, if a Möbius transformation fixes 3 points, it has to be the identity. Because if you give me 3 different points, there is exactly one linear transformation. If you give me 3 different points, there is exactly one Möbius transformation sending the first one to the first one, the second one to the second one, the third one to the third one. Exactly one. And I know one that does that, which is the identity. So if a Möbius transformation fixes 3 points, it is automatically different points, then it's automatically the identity. That means that if you give me a non-identity Möbius transformation, it has at most 2 fixed points. A third fixed point would tell me it's the identity. This is kind of one of the keys that are going to allow us to start with an arbitrary Möbius transformation, and from that arbitrary Möbius transformation be able to read a standard example. The fact that for every Möbius transformation I know, there are at most 2 fixed points. For every non-identity Möbius transformation. Well, some exercise. You see, I mean, I think it's nice to try to program what we did here. By the way, here I read these matrices, but it doesn't mean that these are the only matrices doing the job, right? I mean, here I can put 2, 2, 2, 2. And actually, what I know is that I can multiply by any non-zero complex number, and I obtain the same Möbius transformation. So this was just kind of the one that I could read obviously. Okay, now circles go to circles, which before going into the proofs, what is it going to be good for? Well, in the case of in the standard examples, except for the loxodromies, right? That is for translations and multiplication by alpha, where alpha lives either in the unit circle or in the positive real numbers. In those cases, the families of curves I found were actually were these rays and circles, right? and straight lines in the case of the translations. If you think about it, all such curves are simply circles in C bar. Well, I mean segments of circles in C bar. So these circles go to circles. The way I'm going to use it later is I'm going to push using a Möbius transformation, and I know that circles go to circles. So I am going to know how the curves look like for my arbitrary Möbius transformation. That's how I'm going to use it. Okay. Right. I mean, and then here in the standard examples, we did the observation, right? Any standard example sends circles in C bar to circles in C bar, even if those circles are not centered at the origin. Okay, and then there is one special Möbius transformation, which is which is 1 over z. Z goes to 1 over z, and that one sends circles to circles. Okay, right. So this one here sends z to 1 over z. All right, and then the way I'm going to prove it, there are several ways to that one can prove it. One can actually prove it only using only synthetic Euclidean geometry. I mean, without any kind of complex analysis or anything. But I'm going to do it kind of in a lazy way. I mean, I'm going to use the fact that we know that the serographic projections send circles to circles. And then what I'm going to observe is that this composition. So at the level of the sphere, you see, if you go from the sphere to C bar, from the C bar from C bar to C bar using this mu of this matrix, and then go back to the sphere with P inverse. This one can see that its rotation of 180 degrees around the x-axis, and being such a rotation, it sends circles in the sphere to circles in the sphere. Right? It's kind of obvious, right? I mean, circles in the sphere goes circles in the sphere. And if you know that, then okay, then just multiply with, compose with P and with P inverse. This one has to send circles to circles because P sends circles to circles. Okay, so somehow somehow a proof will follow if we are able to show that this one is some rotation around some axis. Right now, let me kind of just kind of maybe wave the hands as to to convince you that this is the 180 degree rotation. Notice that it is possible to just compute, right? I mean, kind of to take x, y, z on the sphere, apply P through the formula of the stereographic projection, and then invert as complex number, and then go back with the other formula of stereographic projection, and then check that this is indeed the rotation of 180 degrees around the x-axis, because that rotation has a very easy formula. Right? So showing this, that this is this rotation, is actually easy to do, and that's why I'm not going to do it. I mean, I'm just going to kind of argue. So here in this picture, notice. So here I have, for instance, this part of the sphere, this curve, right? So let's say this curve traversed this way. When I project, what I obtain is the interval 0, 1 traversed that way. Yes, and then when I invert, what I obtain is the real numbers greater than 1, but in the opposite direction, right? Okay, and then when one rotates, right? No, not when one rotates. Okay, and then when one takes again stereographic projection, what one obtains is this other curve, but traverse this way. Right. So was the process clear? Yeah. And notice that it's a coincidence, right? I mean, this curve under the map I'm talking about, under this composition that I'm talking about, turns out to be this one, which is the image under 180 degree rotation. Was it clear? Yeah. Let's say experiment now. Let's say with this red. So this is the negative number, the negative real numbers smaller than -1, and let's say I start with this curve. Sorry, with this curve, right? I project stereographically, so I obtain these negative numbers less than -1, traverse that way. When I invert, I obtain this interval, but traverse the other way. And when I project back to the sphere, right, what I obtain is this one. So the comparison between the first one and its image, it turns out to be rotation by 180 degrees around the x-axis. Let's do one more. Let's say let's say here, let's say here, right? So let's say this. Which one do I want? I think I want this whole one untraversed that way. Right? Its image on the stereographic projection is the positive imaginary axis, traversed in the increasing direction. When I invert, well, the inverse of I is minus I, and from that I can read the rest. So it's actually this when I take 1 over z. And when I project back, I get this curve, but yeah, in this direction. If I'm not mistaken, did I make a mistake? I think it's correct, but something is off, right? Yeah, so let me do it again. Yeah, sorry, I may have done something wrong. So this one traversed, let's say, this way. It gets away, right? Yeah, it gets away. And then when I invert, if I project from the top, I mean, because somehow the point is that the unit disk goes to the lower, to the south hemisphere, right? So going from south to north is really going away to infinity, right? Okay, and then I invert, and then right, it's because I invert. Yeah, no, okay, so that's where I made the mistake. Because I invert, but somehow the inverse of 2i is minus 1/2 of I, right? So it's really this way. Yeah, I should really do kind of maybe do it in two intervals, right? Like, let me do it in 2 intervals. Let's say from here. Let's say, yeah, just this quarter of circle, this going this way, goes to this going to infinity. When I invert this, I start in minus I, but I tend to 0. Yeah, so that's the point. I tend to 0, and then when I stereographically project, I go to the southern hemisphere this way, right? And the final result, yeah, and that looks more like a 190-degree rotation, yeah, around the x-axis, right? And then, well, the rest, right? And so, of course, this is not a proof, but it's kind of, at least it's like a kind of, it starts to convince, right, that it is 180-degree rotation. Okay, and then otherwise, as I said, you can just plug in the explicit formula. Okay, and now let's show that every Möbius transformation sends circles in C bar to circles in C bar. So I take any matrix, and 2 cases, gamma different from gamma equal to 0, gamma different from 0. So when the gamma is equal to 0, so the point is gamma is 0. So it really looks like it can be written as a real scale, as a homothéty followed by a translation, right? So that's what I do. Right? So I write it that way. But you see, multiplying by a non-zero complex number sends circles to circles. I mean, it's a standard example, right? This is a standard example, and this is a standard example. And we already know that standard example sends circles to circles. So in that case, mu of A sends circles to circles. And then the other case, so suppose gamma is not 0. And then somehow what one does is kind of one writes kind of the formula in a clever way. Right? So this mu A of z is, as we said, equal to this, even with the conventions that non-zero complex number divided by 0 is infinity. And you see, somehow somehow the point is that one tries to make the determinant appear. That's somehow what one tries. And when one tries to make the determinant appear, then one says, okay, here I have alpha. Let me try to explain it better. You see, the determinant is alpha delta minus gamma beta. And also, so one tries to force the determinant to appear. So one says, here I have beta, so I'm going to multiply with gamma. So one multiplies with gamma, but then in order for this not to change, one multiplies also in the denominator. Okay, and then one has gamma, and then one forces the determinant to appear by subtracting minus alpha delta and adding it. So somehow kind of that's the key of that's really the trick, right? But I would agree that it's kind of maybe not it doesn't occur to you in the first 2 minutes, right? I mean, and then one rewrites it. Right. And then you rewrite it this way. Right, and then the point is, once you rewrote it this way, then you can see what's the process that one is following. I mean, z in all these expressions, z appears only here. So one can see that the process is one first multiplies with gamma and translates with delta, then takes 1 over z, multiplies with a non-zero number, and translates. And in all of them, kind of the only one that was missing was 1 over z, but that is what we just did. So mu A sends circles to circles because it's a composition of standard examples together with 1 over z. Okay, now if circles go to circles, well, for sure disks go to disks, right? Because every Möbius transformation is a homeomorphism. So if it already sends circles to circles, so whenever I have, I have a circle, and by definition a disk is one of the two complements, right? Okay, so because it's a homeomorphism, if I take one of the two components of the complement, it has to go to one of the two components of the complement. So disks go to disks. So the image of a disk in C bar under any Möbius transformation is again a disk in C bar. And now the kind of the actual question is, which one of the two, if I take this if I take one disk with its bounding circle, this circle goes to a circle, and this disk goes to one of the two. Which one of the two? How do I determine it? So that's the point. And let's say which way do I determine it? Of course, you can say, well, take any point inside and evaluate, right? And then that way you are going to know. Sure. But I would like to solve the question in a more combinatorial way. Let's say that I just pick 3 points on the circle, right? Kind of 3 points that determine the circle, and then just from their position, and just from their images under the Möbius transformation, I want to know this circle goes to which one, and the other circle, and this disk goes to which one, and the other disk goes to which one. So what I'm saying is this. So suppose that what I know is these 3 points, right? And I know the images, right? And then just from that, I would like to know this one goes here to this one or to this one, right? And now the point is, you see, W1, W2, W3. Let's say that we take them, you know, W1, W2, W2, W3. I take the circle in which that they determined in C bar, and then in the two disks, you see, if you look at the 2 disks, in one of them, W1, W2, W3 appear in the clockwise sense, and in the other one, they appear in the counterclockwise sense. Right? Do you see it? I mean, it's kind of, I'm already thinking that I can pass between C bar and the sphere freely. Okay, so that must be the property, right? I mean, I take let's say that I take the disk in which when I see the disk, they appear in the clockwise sense, which is somehow this one, right? Rather than this one. Notice that in this other one, they actually appear in the counterclockwise direction, right? I mean, this is clear if you see it in the sphere. Okay, and then take their images, and then their images. You see, it could be that nu of W1 is this one, nu of W2 is this one, and nu of W3 is this one. That could be as well the case. In which case, the image of this one is not going to be this one, right? Because here they appear clockwisely, but with respect to this disk, they appear counterclockwise. So the image of this one, if this is the case, has to be this one. But if on the other hand, they appear like, you know, nu of W1, let's say, and then nu of W2, and nu of W3, right? I mean, like actually here it's the clockwise fashion, the clockwise sense. Then I can say that it's this one, right? So disks go to disks, but actually, if you just give me 3 points and then you want to know the 2 disks they determine, right? Because they determine a circle, so they determine 2 disks. How do I know I compute them knowing only the images of this? Well, now I know. Right? I mean, I just look at their images, and I look the disk when they appear in the clockwise sense in the domain has to go to in the image that they to the disk where they appear in the clockwise sense. Okay. And well, I ran out of time, so I think I'm going to leave this for the next for Wednesday.